I'm Mitch Marks, electrification specialist with HBK. I'm going to be speaking about event monitoring in power systems. So in an electric power system, we have some sort of power source. This could be a grid or a battery. Today we're going to look at the grid. And this grid is connected up to certain loads. These can be a grid-connected motor. These could be an inverter. Or this could be a resistive load, like lighting. And all of these loads are going to be affected by that input power. The health of the motor, the efficiency of the inverter, the quality of the lighting are all going to be affected by that input power. Now, whether this is a grid or a small factory or even an electric vehicle, that input power will affect all of the downstream items. Now, in a grid scenario, we have a variety of events that can occur. We could have big loads coming online, like a big machine turning on that dips a power system. We could have generators coming online. We could have tap changes. We could even have a tree falling in Ohio that ripples down the power system and creates outages. Now, all of these events are going to affect that quality of input power. So we might see a little blip in the sine wave, or we might see some harmonic content. That is affecting the input to these devices. That's affecting the health of these devices, or the quality of our light, or the efficiency of our inverter. So we're going to want to monitor many of these issues if they're becoming apparent in our operation of our power system. So many of these events can be seen in electrical signals. For example, if we monitor the RMS of a voltage or a current, we might see a change in the RMS of that power source in the event of something like a fault, in the event of something like a large motor being turned on. This could also affect the power input to our devices. Lastly, it could affect the efficiency, reactive power, apparent power of these devices. So by monitoring the input to some of these motors, these inverters, these resistive loads, we can really start to understand how events in the grid affect our power system. We can also understand our power system by looking at the harmonic spectrum. If we look at the input to each of these devices and we monitor, the first, the third, the fifth, the seventh, the 11th, the 13th, we can look for long-term changes and see if some of these harmonics are creeping up or down. And these changes in the harmonic profile, these changes in the RMS profile, are going to tell us how certain events in the grid are affecting our individual devices. Now, these events don't happen very frequently, or if we're having motor failures, we might not know what the source of the event is. Maybe it's two machines coming on at the same time, and that does not happen all that frequently. So in order to understand what's happening in these power systems, we often need to monitor the voltage and current input to each of these loads for a long period of time, sometime on the order of days, weeks, maybe in months. But what we're going to look for is kind of long-term changes in things like RMS. We're going to look for long-term changes in things like harmonics. Now, monitoring these changes becomes very difficult for days, weeks, months when we have something like an inverter-driven system. So our inverter is often powered by, or our inverter loads are often powered by a PWM voltage, which these PWM voltages are switches that are turning on and off at the kilohertz rate. And to understand that, we often need to measure as high as megasamples per second. Now you can imagine measuring a variety of channels, maybe on a variety of loads, for days at megasamples is an unreasonable amount of data. So what we need to do is we need to be able to take this megasample data and run it through calculations to get to things like our RMS, to get to things like our total harmonic distortion or our individual harmonics. So through math, we can take this megasample data and we can refine it down to RMS values, power values, efficiency values that are maybe at the 100 hertz level. And measuring many signals at 100 hertz becomes reasonable for days, weeks, months. Now, another challenge is that we do want to understand how these inverter signals operate. In the event of a traumatic event in the grid, we might want to measure that high sample rate data? Well, fortunately, there are options where when you're measuring, you can monitor a signal, and when you see an event, you can execute a trigger. And this trigger is going to say, okay, I'm going to record mega sample data in this short window so that I can take this data back for analysis. So in your measurement, you can take this high sample rate data, refine it into some smaller segments of calculated data, but also trigger on certain events so that you can use that high sample rate data in further analyses. Now this might sound challenging, taking days worth of data, given these high sample rates and the need for triggering. But fortunately, HBK has a product called eDrive, which can help you in your grid monitoring, which can help you in your power system monitoring. So the eDrive system has a really great ability for data reduction. We have a real-time formula database where we execute things like RMS equations, power equations, efficiency equations in a discrete time digital signal processor, and we can store just that slow rate data, but have that high sample rate included in it all. So we're using that high sample rate to calculate these values and then just storing these values. So we can really reduce that data. And we have the ability to store data for as long as you have hard disk space. So if you want to store it for days, weeks, and months, it's an easy ability because of these data reduction tools. The eDrive system also has a wide variety of trigger options. We can trigger on real-time signal events. We can trigger on RMS values. We can trigger on calculated values, or we can take external triggers if you have a machine powering on or off. This allows us to take that high sample rate data and start to understand what's happening in the grid that might be causing failures in our individual components, or understand what our individual components are doing that's caused by the grid. So these triggers allow us to incorporate that high sample rate data with those calculated values. Lastly, we have experts at measuring and monitoring these types of systems. This is likely not your primary job, understanding how these things fail. Fortunately for us, and for you, we have a wide variety of experts who can implement our tools like eDrive, do these days worth of monitoring, and start to understand how these things are failing. And this could be by monitoring temperatures, monitoring noise, monitoring vibration, and correlating that to the electrical signals. Thank you for your time.